Well, good afternoon. This is 2:09 p.m. on Monday, the 18th of September 2017. It's supposed to be a differential equations class, but right now I'm the only one in the room. Don't know where everybody is. I do have a couple of announcements. It affects one of you. I'm not going to say which one. Hopefully you'll know. But I was supposed to print out the thing from the Vice President statement that we're supposed to read verbatim, but my printer's not working because the cartridges are out, and I just went down to my office to get something to drink, and I saw that they had delivered printer that's supposed to go to the Birmingham campus to this campus, and I think that means they probably delivered the cartridges that were supposed to come to this campus to the Birmingham campus, but we'll see. Anyway, that was part of the hang-up. Then a student came by my office. Came by my office. I had to get a book for her and other things, so that's why I'm running a few minutes late, but still nobody's in the room. Okay, but anyway, the announcement that I was going to make is, and I didn't because my cartridge is not working, is that as of Wednesday, this coming Wednesday, day after tomorrow, they will be removing all unpaid students from the roll. Okay, like I said, one of you is, at least last week, Friday I think it was still listed as unpaid, so please get your payment completed by Wednesday, preferably today or tomorrow, but by Wednesday. Now, if there's some reason you can't, but you know that's in the works, and it's, you can show the business office, the cashiers, something that guarantee that you are going to be able to make the payment sometime, but just not by Wednesday, please let them know that, because I think there's some way they can put a flag on your account so they don't remove you from the class. But if they do remove you from the class and you get the payment done, I think you can sometimes get back into the class, but it's just a lot of extra work for you. So I would say do it now rather than wait till later. Okay, so the sooner you can get that cleared up, the better. Okay. That's all the announcement. By the way, if any of you are wanting to participate in the math team, we are not meeting today. Well, if you want to meet today, I'm here, okay? But the time that we had set aside to meet was right after this class, 3:15 to 4:45. If you wanted to meet then, I will be here. But if you don't want to, hopefully it'll be next Wednesday and then all the Mondays and Wednesdays up until that first week in October, and then that's when the math tournament is at Shelton, so we won't be meeting after that. But we were going to meet today, but the woman that was going to be coming, she said they called a meeting on the Birmingham campus, so she's got to be there at 3, so she's not coming back here until later. All right, and if they may even have a practice there. So we're in Chapter 2, which is first-order differential equations. We are in Section 2.1.2. Well, we're in 2.1, which is solution curves without a solution. And in 2.1.2, subsection here, we're doing autonomous first-order differential equations. Okay, that's sort of a big word, okay, and what do we mean by that? Back in Chapter 1, Section 1.1, we divided the class of ordinary differential equations into two types, linear and nonlinear. Now consider briefly another kind of classification for ordinary differential equations, classification that is of particular importance in the qualitative investigation of differential equations. An ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. Okay? If the symbol X denotes the independent variables, then the autonomous first-order differential equation can be written as F, where is my pen? There it is. All right. F of y comma y prime, that's y in the first derivative, is equal to 0, not equal to some function of x. Or in the normal form, dy dx, that's your y prime by the way, is equal to f of y with no x dependence. That makes it autonomous. Okay? And we'll assume that the function f here is and its derivative f prime are continuous functions on some interval I. Okay? So here's an example. dy dx is equal to 1 plus y squared. Okay? There's no x dependence there. That's your differential equation. Okay? Autonomous differential equation. Here's another one. dy dx, or y prime, I started to say, or y prime, and I typed a y rather than x. So, okay, let's try that again. dx is equal to 0.2 xy. Is that an autonomous differential equation? No, because it has x dependence in the function. The first one, autonomous, the second one, not. Okay? Now, many differential equations encountered in applications are equations that are models of physical laws that do not change over time are autonomous. Okay? Here are a few examples. dA, usually that stands for amount. dt is equal to Ka. Okay? So the rate of change of the amount is proportional to the amount that you have. Guess what? Not dependent on time, so therefore that's autonomous. Okay? Here's one. dx dt, usually that referring to a velocity, doesn't have to. It could be other things. Equal to kx times n plus 1 minus x. Okay? Now, that's an n, not an h. Doesn't matter, it's just some number, but in the book it was n. So I'll put it as an n also. Now, n has nothing to do with t, and this is autonomous. It's quadratic in the dependent variable x, but doesn't have any t dependence at all. Okay? Here's one with temperature. How is the temperature changing with time? And if the differential equation tells you that's K times T minus Tm, where Tm is usually the ambient temperature, guess what? No time dependence there, only temperature dependence. That's autonomous. Here's another one with the A in it. dA dt is equal to 6 minus 1 over 100A. Okay, whatever that's standing for, the amount, the time rate of change of the amount depends only on the amount, not on the time. Those are autonomous equations. Now, all these things, your K's, your Tm's, your N's, those are all constants. Okay, so there's no time dependence there either. And those that we did back in section 1.3, examples of applications of differential equations, they say here every one of those was autonomous. Well, good. A 10 o'clock scholar. Why do you come so soon? Okay. Glad you're here. Okay. Let me turn on the projector and flip the lights. decide anything about math team? I was going to say we would be meeting at 3:15, except that Jasmine, who's also participating, said they called a meeting at 3 o'clock on the Birmingham campus, so she won't be here. So we're not meeting today, but I wanted to let you know. Now, I announced this earlier, and since you came in, you may not go back and hear it on YouTube, so I'll say it again. Doesn't pertain to you, okay, because you have paid. But there is one person in the class who hasn't paid, and the vice president came out with an email someday last week. I saw that he had sent the email, but I didn't have a chance to read it until, I believe it was Thursday, late Thursday or Friday, sometime in there. No, actually, I heard someone said something to me about it on Thursday, and then when I got to read it on Friday, my printer's not working, so I can't print it. I'm supposed to read you what it says, and I haven't been able to take it down to a place to get it printed somewhere else. So, but basically, they will be removing all unpaid students by Wednesday, day after tomorrow. Now, the reason I'm telling you that is in case you have any friends, classmates, anyone else you know that may have not completed payment yet, please let them know. They are going to be removing people from the roll on Wednesday. Now, if you know of someone that is the case for, but they're in the process of getting something worked out so they can complete payment relatively soon, but maybe not by Wednesday, they need to let someone in the cashier's window, the business office know, so that I think they can sometimes put a flag on an account and not remove the student from the roll. I don't know if they're doing that or not, but I've known of them doing it sometimes in the past. So please, if the person that you know may not have paid yet, but is in the process, but just won't be ready by Wednesday, please let the business office know, and maybe they can avoid all the hassle of adding back and that kind of stuff. So anyway, we're on page 39. It's section 2.1, subsection 2.1.2, autonomous first order equations. And we just gave some examples of those. An autonomous first order equation can be expressed two ways. Either that the function of y and y prime is equal to 0, that's one way to say it. The other way is dy dx is only a function of y, no x dependence, no independent variable dependence. So this would be an autonomous equation. This would not, because there is x dependence there. This would be an autonomous because there is no t dependence. It only depends on the amount. This one only depends on x, not on t. This depends on temperature, but not on time. So that's autonomous. That one depends on amount, but not on time. These are autonomous differential equations. I was just saying before you came in, section 1.3 that we went over all the different examples of uses, applications of differential equations. They happen to say every one of those were autonomous. None of those were time dependent or dependent on the independent variable. Okay, so that being said, now they introduced the concept of critical points. Okay. I apologize for my voice. I went to the football game on Saturday, so I yelled too much.
Is this kind of like
It is a little bit, yeah, because all we're doing is with derivatives. But soon we'll be in one of the techniques, some of the techniques we use to solve these, we'll be doing integration as well. But yeah, this is extending that. In fact, one of the things, primary ways we'll do it is separation of variables. You want to integrate both sides. So in that sense, it's a little more like Cal 2. But yeah, but so far this is a lot like Cal 1. All right, so let me erase all this ink. And then the critical point certainly is like Cal 1. Okay, so yeah, I see where you're coming from. The zeros of a function f in that equation I just erased, dy dx is equal to f of y, are of special importance. Let me write it down again. Dy dx is equal to just some f of y. No independent variable dependence. So the zeros of that function, where f of y is equal to 0, they would be of special importance because where they're equal to 0, the first derivative is equal to 0, because that's what it's equal to. Okay? And they would be critical points, okay, of that autonomous differential equation. Okay? A critical point is also called an equilibrium point or a stationary point. Have you seen a wave function generator? They have one at McLean Center. Okay? When you see a standing wave and it has a bunch of nodes, but everything is 0 there, and then a bunch of nodes and everything is 0 there. The nodes are the thing where there's 0. You can have a whole series of waves here, but it's always stationary there. A whole series of waves here, but stationary there. Those nodes, those would be your critical points, where the function is 0. Okay? That's why they would call them equilibrium points or stationary points as well. Now observe if we substitute the constant function y of x equals c into this. Okay? Well, certainly dy dx is going to be 0, and that would be the places where your f of y was equal to 0 as well. Both sides of the equation are 0. That means if c is a critical point, then y is equal to c is a constant solution of the autonomous differential equation. Okay? Not too earth-shattering there, is it? A constant solution, y of x equals c, is also called the equilibrium solution, and equilibria are the only constant solutions of that. Okay? As was mentioned already, the non-constant solution, y is equal to y of x, is increasing or decreasing determine the sign of that derivative. So we've already done that. So let's look at example 3. Erase this again. That wasn't very much, but just to keep from making it confusing. Here's a differential equation. dp dt is equal to p times a minus bp. Okay. Now what they tell us here, a and b are greater than 0. Positive constants. Okay? Now, that's certainly a function of p alone, because a and b are constants. There's no time dependence on those. So this is a function of p alone. Okay? Where t was, forget that, just t is your independent variable, p is your dependent variable. Okay. Now, if we were to set this equal to 0, which means p times a minus bp is equal to 0, that obviously has two solutions, right? P is equal to 0, or P is equal to A over B. By that? I skipped too many steps. Or A minus BP is equal to 0, right? If two factors are equal to 0, one or the other has to be 0. That's pretty much a trivial solution, but it is one. This one, solve this, add BP to both sides. I talk, but I can't write. Okay. And this would be A is equal to BP, and then divide both sides by B, and you get P is equal to A over B. Okay? So those are your two solutions that come from that. And that's autonomous. Those are your two critical points, you might say. Okay, now, just pointing something out to you. Obviously, B can't be 0, right? You can't divide it with 0. Okay. But you see, if B were 0, then A is equal to 0. So this is just P's equal, that gives you the solutions anyway. Okay? That would be, that wouldn't give you an additional solution. P is equal to 0 would then be your only possible solution. Okay. So those are the two critical points. P is equal to 0 and P is equal to A over B. Now, if you think about graphing, and that's what we're doing now, the section is solution curves without a solution, okay? That's what this section is called, 2.1. Normally, the independent variable is the horizontal axis, and the dependent variable is the vertical axis. So in this case, P is on the vertical axis. So P equals 0 would be this line right here, okay? And remember we said both A and B were positive, so A over B is positive. So that would be somewhere up here. This would be the point A over B. Now certainly if B was a great deal less than A is, A over B is a pretty large number. If B is a number less than A, then A over B is a smaller number, less than 1. If A is equal to B, then that happens to be the line Y is equal to 1, or P is equal to 1. Okay. So, what you usually do is, those are your critical points, and what you do is evaluate what is the function doing as it's approaching A over B. We know P is equal to 0 at those 2 points. I'm sorry. The function is equal to 0 at those 2 points. Or the derivative is equal to 0. I guess that's the best way to say it. Is equal to 0 at those 2 points. So either the function is approaching something here, is approaching there. This is just one possibility. I'm just going to do the one the book does. You may have a situation like this. Well, if this is your situation, you're converging on A over B. It's approaching that from the above and from below. You're not approaching the second one down here. P is equal to 0. In fact, it's going away from that. Now you could flip a couple of those either way, then you can get other situations. But that's what we're going to look at, basically looking at the p-axis and what are you doing as you're approaching one or the other of these critical points. Okay? And this is called a phase portrait, by the way. Okay? Another thing you can tell by this, remember we're saying this is equal to some alpha p. Why they don't keep it just dp dt? That would make more sense. But if that alpha p is decreasing here, then if that sign of alpha p is decreasing, that means your p function, if the sign is negative, the p function is decreasing and the arrow is pointing down. Okay? This would say the function p is increasing here, the first derivative is positive, and the arrow would point up. And down here, it's, again, p is decreasing, and alpha p is negative, and or dp dt is negative, so the curve is decreasing, and it's going away from the arrow is pointing downward. Now those are called one-dimensional phase portraits, or simply phase portraits of the differential equation. The vertical line is called the phase line. Okay? Now, the one we had here, we could represent this way. If you had two solutions, y of x equal c1 and c2, then you must be this. Okay. Why can't they be consistent? I don't know. Let me just get this off of there. That's all we have to say about it. That's called your phase portrait, one-dimensional phase portrait. Okay. Let's clear this, because the next thing they're talking about here are what if you had two places? Something like sorry, my throat is going on me. This is fourth class today, so it's not hanging in there too well. Let's say we had now they're changing all of their notation around. I wish they wouldn't do that. But let's say we're going to go back and call this the y-axis and the x-axis. Okay? Just like we used to always do. Okay. Now, what if at some point x0, y0, you know, say, the slope of that? So you know generally where it's going at that point, that function. Okay? You know it's at the point x0, y0, that right there it is. The function goes through there, and it happens to be a negative slope there. So it's sort of going down there. Okay? Now, if you also knew that you had a critical point, goodness gracious, I can't draw, a critical point here where y of x is equal to c2, and you had another critical point down here where y of x is equal to c1, okay, then you know this function, since it's on the way down, it's got to approach this line here and probably going to approach that line up here. So it's going to be doing that. It's not going to back up on itself. It's not going to go vertical. So it's going to have to approach those critical points, because there the slope is 0. Here you have a 0 slope here and a 0 slope there, or at least it's approaching that as x gets very large, okay? Positive or negative. Well, what that has done is broken you into 3 regions. Let me get the order here. They call this region 1, this region 2, and this region 3. Okay? Now, or subregions. Okay? The entire region that it's defined is R, and this is on some interval that it's defined. We didn't talk about that, but let's just say the interval over which it's defined is from here to there, and that's all. This is your I. You don't go any beyond that, up or down. Okay? That's your region R, defined by the interval on Y. Okay. So here are some points here, bullet points. If x0, y0 is in subregion, one of these subregions, I happen to show it being in R2, whatever subregion it is, and y of x is a solution whose graph passes through that point, okay? So in other words, y0 is a solution, okay? when x is equal to x0. Then it says that the y of x remains in that subregion r sub I, in our case r sub 2, for all values of x. That's basically what I was just saying. It's got to stay in there because if you think about it, those C1 and C2, those critical points, are the place where the derivative is 0. So if the derivative is 0 down here and up there too, it can't get out. Okay? It is going to be approaching 0. I don't know why they are making such a big deal about this. By continuity of f, remember we said that was a condition, we must then have either that f of y is greater than 0 or f of y is less than 0 for all the x's in the subregion. Okay? Either or. Now remember what our f of y was? That's the slope of your derivative. I mean, that's the slope of the derivative. Here, they're all negative. Okay? If it had been going in the other direction, they would have been all positive. Another way of saying that, they're monotonic. Okay? Within the region. Okay? F of y cannot change signs within a subregion. And there's a problem coming up at the end that you'll see that. All right, since dy dx equal f of y of x is either positive or negative in the subdivision. Now, I have a little bit of a problem with them saying f of y of x, because that then denotes to me that x is a variable in this, and we've been saying all along it's not. But they're throwing that in that even if you have this, it's either positive or negative in a subregion, okay? Then the solution is strictly monotonic, like I said, okay? That is, y of x is either increasing or decreasing throughout that subregion. Therefore, y of x cannot be oscillatory, sinusoidal, or anything like that, nor can it have a relative extremum, maximum or minimum. Now, that y of x, they've been thrown in there now that as an x dependence, is bounded above by the critical point C1. Okay, they've been listing them below. Okay, as either x approaches positive or negative infinity. If y of x is bounded, that is, bounded above or below by two consecutive critical points of a subregion like R2 that we see here, then the critical points have to be on either side of that y of x, like I've shown here. Okay. Seems like it's just saying the same thing over and over. So anyway, let's go back to, let's do example 4, which is example 3 revisited. So let's go back to that. Okay? Now, don't know if you remember, we said this is the p-axis. This was a t-axis, I think it was. Well, yeah, t-axis. And we had p equals 0 was one of your critical points. And this is such a pain in the neck. I do not want that ended. So I guess I have to discard and start it back again. Pain in the neck. Okay. If I had said keep it, it was going to try to save it with that on it, then I couldn't get it off, I think. Okay, let's try that again. Here's your p-axis. Okay, here's your p-axis. Okay, here's your t-axis. And we had p equals 0 was one critical point, and p equal a over b was the other one. Okay, and the illustration had the function was going down there, up there, and down there. Now, they had to have told you that somehow. Okay, they're just giving it to you. Okay, that gives you three regions. They always put this as R3 at the top, R2 in the middle, and R1 at the bottom. Don't know why, but they choose to do it that way. Now, string caught around that. Okay, if this has a value, some value here, they're calling it a P0. Okay, they're calling another one down here a P0, and they're calling another one down here a P0. Okay. Now, if everywhere in this region is monotonically going downhill, then I don't know what it is up here, but anyway, this is approaching and going like this. If this one's going uphill here, then it would have to pass through P0 and be going like this. Okay? If this is going downhill here, it must be, and whatever it does there, we can't tell. It's probably not approaching an asymptote because there aren't any more. This one probably isn't either, so let me correct that just a little bit. This one's just going up. We don't know where. Okay, so that would be the performance of the functions in those. If we know these three places where the function or happen to cross the t equals 0 axis, three different curves there, then this would be the general shape of the functions. Now, if you knew exactly which one was your, say, initial value or something like that, one of those p's or any other p somewhere, it fixes where you are and which curve you're on. But then in the general sense, all of them are going to pass through those depending on your constants or whatever else you have. So, okay, we just saw in region 1, the function is always decreasing. In region 2, it's always increasing. In region 1, it's always decreasing. Okay. Now, if p at 0 is one of those values, p0, then the R1, R2, and R3 we have respectively the following. If P0 is less than 0, meaning you're down here in R1, then P of t is bounded above, okay, by that line there, P equals 0. Since P of t is decreasing, the equilibrium solution is P of t is equal to 0 is the horizontal asymptote for the solution curve. I think we've said all this, so I don't see why I go over it again. Let's move on to example 5. Well, let's see. Seems like they were doing something else here they don't show something for. All right, let's take subregion R1 in example 4, where P of t is decreasing and unbounded below. We must necessarily have that P of t goes to negative infinity as t goes very large. Do not interpret that last statement meaning that P of t goes to negative infinity as t goes to positive infinity. Okay? We could have that P of t is approaching negative infinity as t is approaching some other value t, where t is greater than 0, capital T is greater than 0, is a finite number that depends on the initial conditions. Okay. Well, let's move on to example 5. I thought there was going to be more there, but I'm sorry. They didn't show a picture of it, but they used the example dy dx is equal sine y. Well, it's autonomous because it only depends on y. The function is only y dependent. It has an infinite number of critical points every n pi, because sine is 0 at every n pi. So you would have to have an infinite number of these at negative 4 pi, negative 6 pi, negative 4 pi, negative 2 pi, negative 6 pi, negative 5 pi, negative 4 pi. Every one of those is a critical point, so you have to determine what's it doing in between each one of those. And generally, if it's a sine function, it's pretty well behaved in between there, but that would be an infinite number of possibilities, whereas here we only had a finite. So let's look at example 5. Said that several times. Let's move to it. Okay. No. All right. Goodness gracious, I've got a headache. Here's our autonomous equation. dy dx is equal to y minus 1 squared. What's its critical point? Yeah, when y is equal to 1. That's the critical point. That's where that thing is 0. And it's only got one of them. Okay? So, if you wanted to, this is nothing too earth-shattering here, I hope. Y is equal to 1. That's your critical point. Okay? Now, let's take a look at that derivative. What does it tell you? Tell me something about the derivative. Always positive. Why? Because it's a square. Okay? No matter what value y you put in there, the derivative is always going to be positive unless it's 0. Unless y is equal to 1, then it's 0. So that means the function's increasing here and increasing here. Okay? So in both of the regions here, it's got to be an increasing function because it's positive derivative. Okay. Now, see if it tells you anything else here of importance. For an initial condition, y of 0 is equal to y0, which is less than 1, a solution y of x is increasing and bounded above by that 1. Okay. So y of 0 approaches 1 as x approaches positive infinity. Okay. Now we're talking about somewhere down here, so what I've been trying to figure out is how they chose the x equal minus 1/2. Oh, that's a different issue, sorry. So I was trying to relate this to the figure here, which looks pretty reasonable, but it's not the figure they have up here. All right, sorry. That's all we can say about that. Now here's another one. I think we're going to have to, thought I might be able to use the same thing. I probably could, but let's do over. Here's another function. Y of x is equal to 1 minus 1 over x plus c. Okay. Now that's a one parameter family. Why? You only have one variable here. That's your parameter. One parameter family. Okay. But it's a one parameter family of solutions of the differential equation. Okay, if you go back to exercise 2.2, you'll see that is it. Okay. A given initial condition determines the value for C. So let's say y of 0 is equal to -1. Okay. I don't know. They're treating this as if it's the same as that original problem, which I don't see how it could be, but let's just say we still had that same situation here, that this was x and y, okay, and we were using y is equal to 1 as a critical point, okay. There's nothing here telling us why that would be the case, okay. So let's say y of 0 is equal to -1. So there's 1, here's -1. 0, -1. That's your initial condition. Well, what we understood before, it was increasing here and increasing here. Sorry. Okay. Well, if it's going through this point, and for some reason y of 0 is 2 when it's greater than 1. So here's another y of 0 is equal to 2. There's another condition, and that's when your y's are greater than 1. These are for when your y's are less than 1. Okay, so this one up here, because it's an increasing function, it must follow that pattern.
How do they find C?
What's that?
How do they find C?
That's what I'm. They just pick it out of the air. That's the only thing I can see here. No, they do two different functions here, and that's what I've been puzzling over. Where did they get the x equal 1/2? Or actually negative 1/2. Okay, when x is equal to negative 1/2. Now this is when they change this to make this to be a 1/2, and I don't know where they came up with that. But in that case, if this was your initial condition, it must be doing this. Okay? Now, let me erase. Oh, no, that's not what I wanted. Okay, hit the wrong key. Okay, let me erase this one. Okay. If that was our 0 that we knew there, the other part of the function does not have a 0. Okay? It must be up here. Now, how do we know that? It's an increasing function everywhere. It must be approaching 0 at this line. Y is equal to 1. So it has to be going to positive infinity there. It's like it's going to negative infinity here and going to 0 elsewhere. But it must pass through that point. Now, another situation, and I'm going to change color. What color would you like? Red. Okay. What if this was your point? Yuck. Y of 0 is equal to 2. So you're up here. You're in this region now. Okay. In this case, your y of x 1 minus 1 over x minus 1. Yeah. And your so your x is at x equal 1. There is your vertical asymptote. So now you know you have to be going here. You have to pass through this point, approach infinity there, approach 0 here, and that would fix your second leg of the function to be over here. Okay? Now, there is absolutely no reason, or I can't find how they did it, except let's just say, well, let's imagine they're here. You go by directions you're given, and that was that they're always positive. That goes back to our original function. If your initial condition was here, then that fixes everything here. If your initial condition is up there, it fixes everything there. Okay? This one has no possible solution. This one up here, the black one here, has no possible solution. So, I don't know. It's everything they're doing makes a little bit of sense, but where they came up with that is not at all clear. Okay. Now, let's, in terms of what they've got here, suppose that y of x is a non-consistent solution of the autonomous differential equation that we've been talking about. C is a critical point of the differential equation. There are basically three types of behavior that x of y can exhibit near C. Okay? All right, what we're doing is going back to our portraits, our one-dimensional portraits here. And I think I'll go back to black as well. Okay. So here we have a C. Okay. And here's a Y0. Okay. On this p-axis. Well, they're not naming the axis, whatever it is. If you have arrow down, arrow up, okay, we say that C is an attractor. Both of those have to be going towards C in the long run, okay? If your Y0 was up here, and by the way, because you have to be along that line, it has to be increasing here. There's your vertical asymptote. Anything else that's there is not ever going to cross C, or even go, well, sorry, depending on where else it was, but it can't have another Y0 in this problem, okay? So let's say we have, again, the C here. Let's say your Y0 was up here, okay? This time we have the arrow up here and arrow down here. Now at C, it appears it's a repeller because things have to be going like this. Now, if there's no other C above that, it just keeps going up. If there is a C above it, then it's going to flatten out. Okay, so I should have, they didn't show another C, so I shouldn't have imposed one. So this would be coming along like that. Okay, now, another situation you could have is up and up. This was down, and these are going towards C, these are going away from C. This time the upper one's going away from C and the lower one's going towards C. Where's your Y0 there? If that's your Y0 here, then again, you look like that. Okay? You have no other choice. Okay? But down here, if you had another Y0, or if you didn't, then you're going to be going along like this. Okay? Now, your last choice was, here's your C. Okay? And you're down and down. The Y0 was down here. Then obviously you got to be going down like that. Okay? And whatever that's doing, if there is anything over here, it has to be coming down like that too. But there's no guarantee it will be. So, here are a few definitions here. The critical point C is said to be asymptotically stable. Okay, when both arrowheads on either side of the dot labeled C point towards C, as in this case here. Okay? All the solutions of y of x that start from the initial point x0, y0, wherever that happens to be, sufficiently near C exhibit asymptotic behavior. The limit as x approaches of y. The limit as x approaches infinity of y of x is equal to C. Okay, if both of these are pointing down, wherever they're coming from, they're both, as x goes to infinity, they've got to be approaching C. That would be called an attractor. Okay. When both arrowheads on either side of the dot label point away, like this one, then all solutions to the dot label C, all solutions that start from an initial point x0, y0, wherever that is, move away from C as x increases. So that was going away. This one's coming towards C from above or from below, it doesn't matter. That's an attractor, as x is 1 to infinity. This one's in a repeller. If it starts up there, it's going away. If it starts down here, it's going away. Okay? That's in a repeller. Okay? I'm sorry. That's said to be unstable. Sorry. This is the unstable case. They blow up going either direction. Unstable critical point is also called a repeller. So that, yeah, both names are right. I thought they were. Okay. Now, if one is going up and the other is going, both of them going up or both going down, then this one is an attractor, but that one's a repeller. That's called a semi-stable situation. That one's coming down, this one's coming down. Then you would be approaching C here, but going to infinity here. That also would be semi-stable. Okay. All right, finally, we're through with that. Now let's look at autonomous differential equations and direction fields. We did direction fields before. Now look at those autonomous differential equations. They depend only on the y variable. So you have these critical points where the derivative is equal to 0, and we hit them before. When we were doing this without having to have all these terms with it, we were already doing this. This is not what I want to do. I want to advance. That's what I want to do. Go back. That's what I want. Okay. If we had, this is our critical point. The slopes here are 0. Okay. Then, any point you have here has got to be going away, going away, going away, sort of a repeller type thing. If you're coming in like this, they're also going away, going away, going away, going away. That is your repeller or your unstable situation. Okay. Now, we showed them like this before. Let's change this. Goodness gracious, my throat hurts. So here we have y equals 0 is a critical point. So we have horizontal slopes here. Okay. And we have y equals 3, a critical point. So you have horizontal slopes there as well. Okay. Now, they are listing R1s, R2s, and R3s again. So I'm assuming they're using the same as before, R1, R2, and R3, though they're not really specifying it, but it looks like that's the case. Okay. I can't see anywhere in here where they tell you what the directions are. They just show you in the figure. If indeed the direction field here are negative, then everything here has to be heading down away from that. Okay? All the curves. Okay? Here they're indicating they're positive, so they would be going like this. Okay, curves like that. Here, they're all negative again. So they're going like this. Okay? Now, obviously, this is your stable case. This is an attractor. Y equals 3. Y equals 0 is a semi-stable case. We're going away from it up here, but going away from it in both directions. So that would seem to be the unstable case of repellers. Okay? But in that region R2, everything's bounded above and below, so it's not blowing up anyway. Now, what you have to do is, is it time? You're right. Sorry about that. Okay. That finished 2.1 basically. Homework exercises here do 1 or 3 or both. Do any of the odds 5 through 11. Do 13. Do 15. All right, that's in 2.1.1. 2.1.2. Do 19. Any of the odds 21 to 27, and do 29. All right, and that's the other. You can look at some of the others if you're interested. Go for those. You've already done your paper topic, so I'm not going to mess around with saying, here's a potential paper topic. You already did yours. So we'll start next time with separable equations. Finally, we get to solve some differential equations rather than being in esoteric land looking at where things may be going without solutions. I like for them to have solutions. So we'll start with separable equations. Fantastic. Next time. So let's get this